Welcome back to my channel. Today we are going to learn about minor, cofactor and determinant. So the minor is the determinant of a smaller matrix of a square matrix. In the sense, let's say if you have a matrix like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is a 4, 13, 14, 15, 16, let's say. This is 4 by 4 matrix. This 4 by 4 matrix of this, of the square matrix, you can remove any of the row or column, row and column. So that will what will this become? This in turn will become 1, 2, 4, 5, 6, 8, 13, 14, 16. It will be it will also be a square matrix, but one less in size. This is 4 by 4. This is 3 by 3. So such a matrix, such the determinant of this matrix is called minor. So first minor, there's a differentiation. Let's say first minor is the uh, determinant of matrix uh, 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 obtained by removing first row and column. One row, one column from just one row and one column. If you remove, um, and the use of minor is to compute what do you call cofactor. Minor is to compute inverse of matrix. Okay, so if you have a matrix, then if you have a matrix, then to, to come up with the inverse of that matrix, you need cofactor. Okay, how we will compute the come up with inverse of a matrix? Let's see now. Now uh, we have a matrix, square matrix, let's say. In that, actually the symbol which represents the what do you call um, first minor uh, first minor is, let's say, ith row and jth column. If you remove these two from this matrix, let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, the same matrix. So we could have used that as well. But if you remove this second row, that is I, 2, and third column, then 2, 3. This the submatrix is represented by M minor matrix 2, 3, let's say. So this 2, 3 will be like 1, 3, 4, 5, 7, 8, 13, 15, 16. So because we removed this row and this column, so resulting in this matrix, which can be denoted by that symbology. And the I cofactor is obtained by that is capital. So these markers are giving a hell of a time for me. Basically, some are bit erasable, some are dry erasable, and they need lot of cleaning. So I'll have to do something about these markers. Day by day, this is getting a big problem for me. Cleaning, please bear with me. Right now, so what is cofactor? This cofactor is given by minus 1 raised to, we have this, we had this, uh, the other matrix that we got by removing ith and jth, uh, ith row and jth column. This cofactor is given by I plus j. Minus 1 raised to I plus j is a cofactor. And when you multiply, now, the yeah, cofactor into actually sorry, minus 1 into raised to I plus j into this mij will give you cofactor. Cofactor is equal to minus 1 raised to I plus j uh, times m I j. Right? So the application of cofactor. Why do we need a cofactor? Is the one purpose is to, as I already told you, to come up with inverse of a matrix. The To do that, we should first compute the cofactors C11, C21, like that, Cn1, C11, C21, Cmm, where is it? N, M, M, N, M, M. And the inverse will be given by 1 by det A C T. This inverse is given by the transpose of this comatrix, uh, uh, cofactor matrix. We call this cofactor matrix. See, its transpose, if you interchange the rows and columns, then dividing it by determinant of A gives you the inverse of inverse of inverse A. So that is about minors cofactors. Now we will move on to the linear equations. Basically, what are linear equations? We will see. This is also the material, I think. Okay. Now, matrices are mostly used to solve linear equations. Let's say, for example, A is a matrix of size Mn and X denotes a column vector, not column vector. Let's say. We will come back to matrices and the rest of the stuff after studying vectors and tensors. Then it will make more sense. Okay, so n into 1 matrix, into 1. Then Ax equal to B. We can multiply this matrix with the vector. This is matrix, this is vector, and giving something else. So this is equal to a a a11 x 1 a12 x 2 a1 n x n equal to b1. Similarly, a m1 x 1 a m n b x x n equal to b. Yeah. B, B, M. So how do we solve the equation Ax equal to B? So what will be x here? If you take x, A on the other side, that will become A inverse B. So you can compute the inverse of this matrix and multiply it with B. That will give you the value of x. Now, uh, yeah, and next we'll go to the square matrix where we have uh, types of square matrices. Square matrices types. Square matrices can be a diagonal matrix, meaning A11, A22, A33, 0, 0, 0, 0. Elsewhere you have zeros. Only this diagonal has the values. So this is the diagonal matrix. Similarly, you can have A11, A21, A31, A22, A32, A33, 0, 0, 0. This is called lower triangular matrix. There can be one more thing which is like A11, 0, sorry, it's the upper one there. So 1, 2, A13, A22, A33, A23, 0, 0, 0. This will be, of course, you might have guessed it, the upper triangle, meaning this is the lower triangle. So we call this lower triangular matrix, and this is the upper triangular matrix. So these are the types of square matrices, and the one of the most important things in matrices is the one of the most important aspects of matrices is are the eigenvalues. We will see what eigenvalue means. Even eigenvalues are also very, very important in theoretical physics in the transformations. So we'll learn about eigenvalues briefly now, and after covering the vectors and tensors, we will come back to eigenvalues. Consider a NN matrix, a matrix with size NN matrix A, non-zero vector V. Then multiplying A with V simply scales V, multiplying A with V simply what it does is scales V, scales meaning scales up V by a factor of lambda, which is a scalar. Then V then V is called the eigenvector of A. V is called eigenvector of A. If you multiply this with factor of lambda, which is a scalar, then what you the V you get is the called the eigenvector of A. There's a basic definition of eigenvector, but we'll go deep into this later because right now it doesn't make sense without knowing what vector is. It doesn't make sense to know further about eigenvalues. Now let us go to determinant. Determinant is denoted by that A is a matrix, then the determinant is denoted by det det A or yeah that or even det is uh, even like that you can the determinant of our square matrix, let's say 1 2 3 4, or even the other variables. We take variables. This doesn't make sense. So we'll take A, B, C, D, let's say. Then you have to multiply these two and you have to multiply these two. AD minus BC will be determined det det A. So this is, let's say this is A, this is det, right? So that's the determinant, and as we have seen the eigenvalue AAV is equal to lambda V. We are multiplying with lambda the eigenvalue, and that A minus lambda I is equal to 0. That's one identity. Determinant of A minus lambda I identity matrix, if you take, that should be 0. This is very, very useful in solving problems. So Um, yeah. For today, we will call it a day for now, and then we will next class we will learn about basically we'll start vectors, then we'll go to tensors, and then we'll come back to these some of these solving linear equations. We will come back to that later. Okay, so thank you for watching my video. Bye for now.